Well, class, this is the study guide for Test 4 on radical and rational equations. And what I'd like you to do is to copy down what I've got on this study guide and then pause it, listen to my instruction, continue to copy, pause, and replay as often as you want it. And when you get home tonight, look back over it again. I'll do the best job I can explaining how to do these things. So to begin with, number 1, we've got a function h of x is equal to square root of x plus 2 plus 1. We're used to seeing y on the left-hand side. Don't let that confuse you. The first thing you want to do is you want to graph it. It's going to start at -2 because remember, a square root equation has to start at 0. It can't go below 0 because that would be negative, and you can't take the square root of a negative. So it's going to start at -2 and up at +1, and then it's going to go this way. Now, the y-intercept, I hope you can tell, is right here, but how do you get it? Well, a quick way to do it is just hit the trace button, and you'll land on about 2.4, which is just about right. The other way to do it is to put a y here and a 0 there. And so you get y is equal to the square root of 0 plus 2 is 2. So take the square root of 2, add 1 to it, and you'll get 2.4 also. Now, in this case, there is no x-intercept. It does not cross the x-axis. The domain, in terms of x values, they start here at -2 and they go to positive infinity. The range, the up and down values, start here at 1 and go up forever. Increasing, we haven't really dealt with that much, but I hope it'll be obvious that the curve is increasing. It's going up from this point to the right. Does it ever go down like a parabola? No, it does not, because this is a square root equation. And that's number 1. Let's scroll up to get to number 2. And again, pause and copy down however you want, but here's my explanation for number 2. Here we have a rational equation. This is where it's undefined when x is 0. So this will be your vertical asymptote. Coincidentally, it's the y-axis, but it's the x equals 0 line. Similarly, there is no other number indicated to the right of that, so the horizontal asymptote is right on top of the x-axis. Because it's positive, we have branches here and here. There is no y-intercept. There is no x-intercept because these branches, they never actually touch the asymptotes. I've mentioned the vertical asymptote, the horizontal asymptote. The domain. Now, because you've got arrows to the left and arrows to the right, all x values will ultimately be included except when you get right there. And that's why this thing dashes down and splits, because there is no x equals 0, because that would make it undefined. So we'd say the domain is all real numbers except 0. The same deal with the range. You're coming up, but once you get to where y is 0, it slashes to the left and to the right, and so it's undefined right there. The increasing and decreasing with rational functions is hard to think through, but this is going down, it's never going up. All right, let's go down to number 3. And let me move the camera a little bit here. I guess that's still there. All right, here we have a binomial times a binomial. Same old stuff. We go 2 times 5 is 10. 2 times -2 onto the square root of 3. You multiply that 2 by that -2, but not by the square root of 3. You cannot multiply an outside number by a radicand. -3 square roots of 5 is, -3 times the square root of 5 times square root of 3 times 5 is 5 square roots of 3. In a moment, we can combine those. And square root of 3 times negative 2 square roots of 3 is negative 2 square roots of 9, which we know will reduce. And so we combine negative 4 plus 5, we get positive 1 square root of 3. Negative 2 square root of 9 is 3, so you have 10 minus 6 is 4 plus the square root of 3. All right, number 4, we're going to combine these, add or subtract, but we have to break them down. You cannot add or subtract unless they're like radicands. So 8 becomes 4 times 2, 32 becomes 16 times 2, and square root of 2 is in simplest form. And so the square root of 4 is 2, square root of 16 is 4. 2 times 2 is 4 on that square root of 2, minus 4 times 4 is 16 onto that square root of 2, plus square root of 2. So we've got all square roots of 2, so we have positive 4, take away 16, which would be negative 12, plus 1 would be negative 11 square roots of 2. All right, number 5, we've got to break down 108. Again, use your calculator, do y equals 108 divided by x, then go look at the table to find the largest perfect square. Turns out it's 36. So 108 breaks down to 36 times 3. Any even power is automatically a perfect square, so x4 is a perfect square. The square root of x4 is x2, which we'll get to in a moment. Now, y5, an odd power, cannot be a perfect square, but we break down y5 to y4 times y1. And then z to the 1 is in simplest form. So, square root of 36 is 6. We have 6 square roots of 3. Square root of x4 is x2. Square root of y4 is y2. Square root of y is still square root of y. Square root of z is still square root of z. And you put everything that's outside the radical sign out front. So you have 6x squared y squared. And then under the radical sign, we've got 3yz. And so that would be example 5. All right, let's go to the next page. Now here we're solving radical equations. You must try to remember that with radical equations, you can sometimes get a correct answer that when you plug it in to check, it turns out to create a false situation. And if that ever happens, that one is what we call extraneous or extra. Doesn't count. It's not a valid answer, even though it came out through your algebra. So here we'll subtract 5 from both sides. It's already a square root, so we'll square both sides. 2x plus 1 equals 9. Subtract 1, we get 2x is equal to 8, divided by 2x is equal to 4. But well, that's a perfectly fine answer algebraically. If we plug 4 back in here, watch what happens. 2 times 4 is 8, plus 1 is 9. What's the square root of 9? 3. Is 3 plus 5 2? No, it's not. 3 plus 5 is 8, and 8 does not equal 2. So there is actually no valid answer. That is extraneous. Number 7. Again, the trick, we have to get rid of the square root operation, so we square both sides. But notice that when you square a binomial, it's not just x squared minus 1 squared. It's x minus 1 times x minus 1. So you have to distribute that out, and now we've got a quadratic equation. So I'll subtract 5x, add 9, and we have this trinomial, and fortunately it factors into x minus 5 times x minus 2, because negative 5 times negative 5, when you multiply is 10, but when you add them, you get negative 7. And using the zero product property, we get x is equal to 5 and x is equal to 2. Now, I've already checked the 5 and I know it works, but watch what happens with the 2. 5 times 2 is 10. 10 minus 9 is 1. What's the square root of 1? 1. Okay, so on the right side, the answer is 1. Over here, what's 2 minus 1? 1. Well, I think that does work. Let me go back and check one more time real quick. See if I may have made another mistake. 5 times 2 is 10. 10 minus 9 is 1. Square root of 1 is 1. And then 2 minus 1 is 1. Actually, 2 is correct. I made a mistake last time I did it. So the answers are 5 and 2. Okay, now we're solving a system of equations. This is a rational equation set equal to a linear equation. And we can do it because they're both equal to y. And y is equal to y. Now the x is in the denominator, so I need to get it out of there. I'm going to multiply both sides by x, like I did here. So we have -1 on the left side, and then x times x is x squared. X times 2 is 2x. Once again, a quadratic equation. I want a 0 on one side or the other, so I'm going to add 1 to both sides. We have a 0 here. And then we have a quadratic equation that does factor very nicely. X plus 1 times x plus 1, and using the zero product property, we get x is equal to -1. And I have previously checked that, and it does work. All right, now number 9, a similar problem said a little bit differently. We got two functions, f of x and g of x. Two different equations, but is there a number for x that will work for both of them? Well, the way you do it is you set them equal, like we do here. Similarly to the last problem, we've got an x in the denominator, so we're going to multiply both sides by x. So we have -5 is equal to x squared plus 6x. Move that 5 over, another quadratic equation that factors nicely into x plus 5 times x plus 1. And using the zero product property, we see that x is -5 and -1. All right, number 10. We have a radical equation, and we're trying to write an equation based on a shift. If we start here and we shift left 3 and then up 9, what equation would do that? Well, you have to sketch it out. So start here. We know it's going to begin at +3 because 3 minus 3 is 0. And again, 0 is the smallest number you can take a square root of. So it's going to start here at 3 and then down 4 and then move to the right. All right, so if we're here and we want to go left 3 units, where are we? Well, we're at x plus 0, or in other words, just x. And if we're down here at -4 and we want to go up 9, so we're at -4, we go up 9, where do we land? At +5. All right, number 11, similar kind of thing, except this is a rational equation. Vertical asymptote is at +2. Again, 2 minus 2 creates the 0. 0 makes that fraction undefined. Now, you'll notice up here we want to define a 0, but for a different reason, because the smallest square root we can take is square root of 0. Square root of 0 is 0. But once again, we're trying to find what creates a 0 here, but for a different reason, because that makes the fraction undefined. So at +2, we've got a vertical asymptote. We have a horizontal asymptote at -5. And here are our branches. Now, if we want to go from here right 5 and down 1, well, where am I right now? I'm at +2, and if I go right 5 units, where will I be on the x-axis? +7. And so we write x minus 7. And then, let's see, let me not get ahead of myself. If I'm down here at -5 and I want to drop down one more, where am I? Well, we're at -6. And that was number 11. All right, number 12, we have the volume of a pyramid with a square base is related to the height, h, of the pyramid, and the length of one side of the square base, s. And you've got this formula. Now, when I was in high school, sometimes I didn't understand all that was being said in the word problem, but once I saw a formula, I knew I had to work with that, whatever the rest of the problem meant. And the same thing is true here. We're trying to find the volume All right, that's up here under the radical sign, so that should give us a clue. Given that a side of the length is 4 inches, so we're going to have a 4 here, and the height is 5. So we plug those numbers in. Now we say to ourselves, all right, well, how do I begin to solve for V, volume? Well, it's under a square root, so I'm going to square both sides. So 4 squared is 16. Square root of 3V over 5 squared is just 3V over 5. Oh, and then all of a sudden it becomes much easier, doesn't it? To get rid of that 5, we'll multiply both sides by 5. 5 divided by 5 is 1. And so we have 80 is equal to 3V, divide both sides by 3. And it turns out that the volume is 26.7 inches cubed. All right, and well, let's just deal with 13 right here. All right, this is a variation problem. The keyword is inversely. The time required to empty a tank varies inversely, so time equals K over R, the rate of pumping. You want to create your equation based on the order with which you read it. It says time varies with rate. Okay, so we got time and rate, and it varies inversely, so the K, the constant, is on the top, not to the side. Now, you take the first situation, it can empty a tank in 2.5 hours, that's time, 400 gallons a minute. We solve for K by multiplying both sides by 400, so we get that K is 1,000. Okay, now that we have our K value, the constant, we plug it into the second situation, how long, so we're looking for time. Inverse, so the K number goes up here. We already know it's 1,000 at 500. So cross that out and you get 2 hours. Let's go on. Now, there will be a review of factoring on this test. Here we have a difference of 2 squares, x minus 3 times x plus 3. Here we have a trinomial with the leading coefficient is not 1. It's not a GCF, so we have to use trial and error. And so, I wish there was an easy way to tell you to do it, but you're going to look for 2 factors of -2, and you're going to deal with those. It could be +2 and -1. It could be -2 and it should be +1. I can't quite read what I put there originally. It could be +1 and -2, or it can be -1 and +2. And you just have to try it out and just start multiplying, see which one works, and it turns out this is the one that works. All right, number 16, we have a 2-term thing, but it's not a difference of 2 squares. So you say, well, what do I do? Well, you take out the GCF. Well, what is the GCF? Well, they both have a 5, they both have an x cubed, and they both have a y to the 1. And then you say, okay, well, what would I multiply this by to get back to there? Well, it'd be y4, because y4 times y1 is y5. Or, over here, you'd say, well, what times this would get me that? Well, 5 times, all right, a -4x. All right, coming over here to number 17, we want to rewrite this with rational exponents. Now, I want you to notice this does not have the parentheses. So what that means is that literally every term in here gets raised to some power. So we want to begin with 27. The cube root of 27 would be the same as 27 to the 1 over 3. The cube root of x cubed would be the same root as x to the 3 over 3. Remember, the index number is always the denominator. Y to the 1 power, the cube root of y to the 1 power would be y to the 1/3. And the cube root of z5 would be z to the 5/3. Now we multiply this stuff together. Turns out 27 to the 1/3 power is the number 3, because it's 3 times 3 times 3. Y to the 1 cubed. What did I do with the x? Oh, okay. X to the 1 power is just x. Y to the 1/3 z to the 5/3. All right, now 18, these are always kind of hard, but you just have to begin somewhere. You want to think of it as up and down. For instance, 24 over 27 reduces to 8 over 9. 8 to the 3 divided by a to the 3 divided by a to the 8. You may want to remember we subtract exponents when we divide, so it's a to the 3 minus 8 or a to the negative 5, which in a moment we'll put that down in the denominator. Okay, b to the 2/5 divided by b to the negative 6/5. All right, so just think of 2/5 minus a negative 6/5. That's 2/5 plus 6/5, or in other words, 8/5. So really the only thing we need to do is we need to move that a to the 5th down below here, line it up with that 9, and so we have a, b, 8 over 5 with 9a5. And number 19, we have a quadratic equation. We want to get a 0 on one side or the other, so I added 2. And then I used the quadratic formula to solve for that. Remember, it's negative b plus or minus square root b squared minus 4ac all over 2a. There, I know you're happy to hear that. But your a, b, and c number, a is 3, b is 5, c is 2, and you plug it in. Again, guys, I've said this 1,000 times. Put these parentheses there. If you do, it's almost impossible to make a mistake. And so it turned out that the discriminant, what's under the radical sign, not counting the radical sign, turned out to be the square root of 1, which ends up being 1. So we're here and we say, all right, well, it's negative 5 plus 1. Well, what is that? It's negative 4 over 6, reduces to negative 2/3. Negative 5 minus 1 is negative 6 over 6 is negative 1. All right, let's turn the page. All right, number 20, we've got a rectangle with these two side lengths, and we're to find the area. All right, well, area is length times width, so it doesn't matter which is length, which is width. We just know we're going to multiply them together. So no biggie, 2 times 4 is 8. Now again, you can't do the 2 times the 10. You can only do the radicand by the radicand. So we get 8 square roots of 50. Well, break down the 50. 25 times 2. What's the square root of 25? 5. 5 times 8 is 40. Square roots of 2. All right, here, find the perimeter. Well, okay, that's the distance all the way around. So if I don't know, let's call that the width. We'll have 2 of those. If that's the length, we'll have 2 of those. So we're adding them up like so. Now, we can add the square root of 5s together. 2 plus 2 is 4. We can add the square roots of 10 together. 4 plus 4 is 8. But we can't go further than that. All right, 21. We've got a house in the neighborhood. It shows the time t that it takes a group of n painters to paint the house. If the time taken to remove the debris varies inversely as the number of students. In other words, the more students you have, the less time. The less students you have, the more time it's going to take. So t for the time it takes, we know it's inverse, so it's k over p. I forget why. Oh, p for painters. That's why I picked that. So time and the number of painters. Now, what is confusing is you've got all these options. All you got to do is just pick one of them. You don't, because since it's the same relationship, they're all going to work the same. So just pick one of these columns. So we set 20 minutes is k over 1 painter. In other words, 1 painter to remove the debris takes 20 minutes, which we can think that if you got 2 painters, it ought to take 10 minutes, and so on. So k is equal to 20. And in fact, they don't ask us to solve anything, they just want the equation. So the equation is that t is equal to the number 20 divided by however many painters you've got. All right, and our last problem, again, you've seen this before. We've got a rocket with that quadratic equation. When will it be 20 feet in the air? Now, I don't mean 20 feet going on the way up, but on the way down. So under y sub 1, you put the equation. Y sub 2, you put 20. You go to the window and resize it until you can see that intersection. In this case, you don't need to see the maximum height because it's not being asked to do that. All you need to see is that intersection. Then you go second calc, number 5 intersect, move the cursor close to there and hit it 3 times. Boom, boom, boom. And at 7.8 seconds, it's 20 feet off the ground. Now go back and replay this video as often as you'd like. Pause, copy all this stuff down, and again, use it at home tonight if you'd like to. And good luck on the test.